Okay, up to this point, we've been talking about populations as something that could be sampled in their entirety. The reality is populations are usually very large, so if you wanted to measure some parameter of a population, such as height, if we're talking about a human population, or length, if we're thinking again about those fish populations, the ability to sample the entire population and determine a true distribution is usually not possible. And so what we have to do is actually sample a population, collect a smaller number of individuals from the population to represent the larger population. So when we're doing parametric statistical tests, as we'll talk about throughout the semester, that's basically what we're doing is we're taking a sample and measuring some parameter of that sample, such as mean, such as the sample's standard deviation, and using that as a proxy for the population's true mean or the population's standard deviation. Okay, so when we sample a population, then there are a few things that we need to keep in mind, and this will be reinforced throughout the course of the semester as we talk more about experimental design. But we've got to think about sampling in a random way, so that we're collecting individuals from the population that are not connected in some way. So the first fish that's collected from a population isn't necessarily going to determine what the second fish is. So in other words, we're not collecting them from necessarily the same area, because that can then bias our sample. So we typically want to use some sort of a randomization process for collecting our sample. We also want to make sure that they're representative. We also want to make sure that we're collecting a sufficient sample size. So, for example, if we have a population of say 1,000 fish, and we collect 3, well, the question then is how well can those 3 actually represent the full population? So we need sufficient sample size to give us some confidence that the parameter that we're measuring in the sample actually is a good estimate of the population parameter. And we'll talk again throughout the course of the semester about how sample size affects our confidence in that estimate of the population parameter. But you can think of it in general terms, as the sample size increases as it approaches the population size, the confidence in the population parameter is going to increase. Okay, so what characteristics of a population will determine if a sample is representative? A lot of times the nature of the distribution of the population will determine how well we can sample the population and have some confidence in the nature of the population parameters. So for example, a skewed distribution may be very hard to represent in a small sample. A sample which has high kurtosis, so it's leptokurtic, may be very hard to represent the tails of that distribution with a small sample size. So typically a classical normal distribution is easier to sample from and easier to represent with a sample. Okay, so as I mentioned before, when we're collecting samples, we're trying to estimate population parameters. So we're going to collect sample parameters such as a mean, sum of squares, variance, etc. And we're going to use these as estimates of population parameters because, again, as I said before, we typically can't measure the entire population. Okay, so some of the things that are going to be most critical here as we go forward into some of the future weeks is mean. Okay, let me just turn my pen back on. Okay, you may be actually wondering why why we're having to turn the pen back on and why I'm no longer wearing the same thing or sitting in the same place as I was before. I ran into a little bit of a technical glitch yesterday, and so I'm continuing this today. But anyway, so the mean then is what we typically refer to, what we typically think of as an average. So it's the sum of all individual observations, and I'm denoting individual observations as xi, okay, minus, a sum of all individual observations divided by the sample size, okay. And again, this is really meant to be representative of our sample, of our true population mean, which is designated as mu. Okay, our sum of squares gives us begins to give us some indication of how much variation there is around that sample mean. So are all the individuals in the population very close to that mean, or do they tend to vary quite a bit from that mean? So our sum of squares for our sample is calculated by x of I, our individual observations, minus x bar, where x bar is our sample mean, and so x bar then is a proxy for the parameter mu, the population mean. Okay, so our sum of squares is just the sum of the individual observations minus the sample mean, all of those values squared and then summed together. Now, it can be calculated a little bit more efficiently as the sum of all xi, or individual observations, squared minus the sum of all individual observations squared. So I know I said that in the same way, but notice that there's a little bit of a difference. In this case, what we're doing is we're taking all of the individual observation values, squaring those, and then summing those squared values. In the second case, what we're doing is summing all the individual observations and then squaring the sum of those values and dividing that quantity by n, or the sample size. Okay, I like you to recognize this formula because I think it's more intuitive. It gives you a better sense of what sum of squares actually is, right? It's the difference between the observation and the mean squared, and then we sum all of those together, as the name sum of squares would suggest. This one, you may find, though, is a more practical formula for calculations. Okay, so it's a little bit easier to apply. Okay, now I should also mention that this is the sample sum of squares, and again, it's meant as a proxy for the population sum of squares, which can be designated or denoted as xi minus mu, the true population mean, squared. Okay, variance. I'm going to actually just clear this screen and come back to it so that we have a little more space to work. The variance, again, a population variance is denoted as s squared, and population variance is calculated as the sum of squares divided by, in this case, rather than n, divided by n minus 1. Okay, and this is meant as this is calculated as a proxy for the population sum of squares, which is denoted by sigma squared. And this is equal to, as you might already understand, individual observation minus mu squared divided by n. Okay, not n minus 1, but rather n. So n minus 1 is a term that we're going to see again and again, which refers to degrees of freedom, and we'll explain degrees of freedom in a later lecture. But this term then this variance is used, sample variance is used as a proxy for the population variance. Okay, now variance by itself doesn't tell us a great deal. What we typically see in terms of measures of variation around a mean reported is the standard deviation. So quite often, if you think about graphs that you've seen, you'll see the mean plotted plus or minus a standard deviation unit. So standard deviation is a very commonly reported parameter that allows us to get some idea of not only the sample mean, but how much spread there is in the distribution around that mean. And standard deviation for a sample is denoted as little s, and little s is equal to, as you might guess, then the square root of s, or the square root of variance. Okay, so I could also write that out longhand as this is equal to the square root of the sum of squares divided by n minus 1. Okay, and again, variance, that population standard deviation, or sigma, would be equal to the square root of population variance. So population standard deviation, or sigma, is equal to the square root of the population variance. Okay. Now, there are a couple of other parameters that I'm going to introduce now, even though in your textbook they don't come up until a little bit later, including confidence intervals and standard errors. Let's start off quickly by talking about standard error, and then we'll come back to the idea of a confidence interval. Okay, a standard error is what this actually is the standard deviation of multiple means. Okay, so for example, let's suppose that I have a population, large population of those fish. I take a sample of 5 fish and I calculate the mean. Okay, I then throw those fish back and I take another sample of 5 fish and calculate the mean. Okay, and I do this repeatedly. So I've got maybe I take a total of 10 different samples of 5 fish each. If I were to take those 10 averages, or those 10 means now, and treat those as my sample, I could calculate a standard deviation of those sample means, and that would approximate my standard error. So standard error then is related to standard deviation and can be calculated by standard deviation as standard deviation divided by the square root of n. Okay, so standard error is denoted as S sub x, so in other words, the standard deviation denoted as S of the means. Okay, so the standard deviation of the means is our standard error, and it's calculated as standard deviation divided by square root of n. Okay, and again, this is a proxy for our population standard error. Where big N represents the total population size, whereas little n represents the sample size. Okay, now finally I'm going to get to the idea of confidence intervals, and I'm going to do this in a little bit of a roundabout way. Let's suppose that we have a normally distributed population. Okay, within that normally distributed population represented by a mean, okay, that we'll call x bar. Within a normal distribution, what we find is that roughly 70%, almost exactly 70% of the total population, and I'm going to shade this so you can see that this area that I'm talking about. This area that I'm shading represents about 70% of the total population distribution. And that's going to lie within plus or minus 1 standard deviation unit. I should be representing this as S since I've given you X bar. Okay, so again, about 70% of the population lies within, oh, my handwriting's getting awful, plus or minus 1 standard deviation of the mean. Okay. If I go out to plus or minus 2 standard deviations, so out to here and here, and let me actually change the pen color now. Now, roughly 90%, roughly 95%, actually it's a little bit more, roughly 96% of the population lies within plus or minus 2 standard deviation units. Okay, and 95% then lies within the range of plus or minus 1.96 standard deviation units. Of the mean. Okay, so what I'm getting at here is that the amount of the distribution, or the amount of the population that falls within certain bounds, within plus or minus 1 standard deviation unit, plus or minus 2 standard deviation units, is predictable for a normal distribution. So quite often, like we can describe populations based on plus or minus a standard deviation unit, or we can also describe them based on confidence intervals. So in other words, how much of the population, how much of a population lies, what percentage of a population lies within certain boundaries. So a 95% confidence interval corresponds to a mean plus or minus 1.96 standard deviation units. If you wanted to talk about a 99% confidence interval, again, that would scale to some conserved number of standard deviation units. I believe it's something like 2.34. So there are these two different ways that we can kind of describe the variation around a sample mean, either with standard deviation units or with confidence intervals, but you should recognize that these are related concepts. Okay, and quite often we're using confidence intervals just to give us an idea of, when we collect a sample, how confident are we that it represents the true population mean. 95% of the time, the true population mean should lie within plus or minus 1.96 standard deviation units of our sample population mean. Okay, so that's what we're getting at. And again, the idea of distributions, the idea of uncertainty or variation around a sample mean is going to be key to when we start to compare populations. Okay, and that kind of takes us into the idea of sampling and probability, and what is meant by a p-value. What are p-values all about? Okay, a p-value really is about the probability that an observation. Well, okay, let me describe it in the simplest terms, the way that we typically use it. A p-value is the probability that a sample parameter, such as a sample mean, actually could have come from a given population. So what I'm getting at, and I'm saying this in a really awkward way, is let's suppose that this is a population distribution. This population distribution has a mean of say 95. Okay, let's suppose that I were to actually go out there and collect a sample. I can't measure this entire population, but I can measure a subset of this population. Okay, I might actually find a distribution. My sample distribution might actually look like this. Okay, my sample distribution might also look like this. Okay, these are a couple possible samples that I might collect from this true population. Okay, so the question is then, what is the probability that a sample with this mean and this distribution could have been collected from this population that's described by the blue line? Okay, or again, what is the probability that a sample with this distribution and with this mean could have been collected from that same population? Okay, every time I collect a sample, it's going to be a little bit different. The sample mean that I calculate, is meant to approximate the true population mean. And so the question is always, how well does it actually represent that true population mean? Okay, so again, the p-value then is the probability that a sample collected, is the probability of collecting a sample from a population and attaining a mean that is this different from the true sample mean, from the true population mean. Okay, so if this is the true population mean right here, what is the probability that I could actually collect a sample that had this much variance or this much deviation from the sample mean, from the true population mean? Okay, or what is the probability that I might have collected this sample with a mean population as low as 50 if this is my true population distribution? Okay, and what it comes down to is we're going to, when I'm talking about sampling a single population, this may seem kind of strange. What is the probability? Well, it's 100%. We know that sample came from that population. But the way we actually apply this in a more meaningful way is when we start to compare two different samples to ask the question, what is the probability that these samples could have actually come from the same population? And what that really relates to is this area of overlap. Okay, so in this case, what we're asking now is not related to the true population mean. Well, it is, but what we're really asking is, what is the probability that if this sample, what is the probability that this sample and this sample both could have been drawn from the same larger statistical population and have means as different as 50 versus 120? Okay, and this area of overlap between the two distributions gives us that probability. So if this is the distribution of sample A and this is the distribution of sample B, this is the probability, this is the area of overlap which relates to the probability that these two samples both could have been drawn independently from the same larger statistical population. Okay, if the probability is high, if the probability is sufficient, then we would say that there's no difference between this sample and this sample. they've come from the same population. If the overlap is extremely low, okay, so now let's look at this area of overlap between the black distribution or the black sample and the green sample. If that overlap is extremely low, we'd say that there's a very low probability that these two samples could have both been drawn from the same statistical population, in which case we'd say that they represent two different populations rather than two samples within the same population. Okay, now that's going to be really important, and just a concept for you to review, because I know it's not intuitively obvious, but it's a concept for you to review from time to time, because when we get into things such as experiments where you have a control group and a treatment group, we know that they didn't come from the same absolute population, but we're going to ask the question, could they have come from the same statistical population? And if they could, then there's no treatment effect. But if the area of overlap between our control group and our treatment group is very, very low, then what we would conclude is the probability that they come from the same statistical population is very small, and more likely they represent two different statistical groups or populations, and therefore there is a treatment effect. Okay, when we applied a treatment, we ended up with a higher value of our observed variable. Okay, so again, we'll come back to that concept again and again through the course of the semester. Okay, so I also want to talk a little bit about transformations, and I want to end on transformations for today's lecture. Quite often, we've been talking about populations and probabilities on the assumption that a population is normally distributed. Quite often, it's not. Okay, so quite often we might get a population that looks like this. Let me change my pen color again. We might get a population that looks something like this, which is right skewed. Okay, the tail to the right is much longer than the tail to the left, typically thicker than the tail to the left. Okay, in this case, what this means is that there are a number of individuals within that sample that actually have a very large value. Okay, much greater than the mean. Okay, there's much less variation around the mean on the small end of the scale, but more variation around that mean on the large end of the scale. This isn't uncommon. We see this type of distribution quite a lot in nature. Sometimes we also see a distribution that looks more like this, where the skew is left. Okay, that's less common, but it does happen. Okay, so quite often what we do with this first type of data, when we see a distribution that looks like this, is we'll do a log transformation, where we take the raw data, the individual observations, the individual values of our measured value, whatever our measured value is here. Okay, whatever the parameters that we're estimating for our population, and we take the log of the individual observation, okay, plus 1. And the reason that I throw in the plus 1 is that way if you have any values, any observations that range between 0 and 1, so in other words they're decimals, you still return a value when you take the log of that value. Okay, so log transformation is something that you're going to find commonly useful. You're going to use it quite a lot to transform this type of data set so that it better approximates a normal distribution. Okay, a power transformation can be useful if you're doing something, if you have a distribution that looks like this. So you might, for example, take your all of your individual observations, individual values, and raise them to some power. And I'm going to just indicate that as a P here. P can be any number you want it to be. So it could be squared, cubed to the fourth. It can be a decimal value, so it could be 1.5. The point here is that this type is that you'll probably have to play around with this value a little bit so that you can optimize the transformation and make this better approximate a normal distribution. Now there are some limits. You know, if you get carried away in playing with this value, you may end up getting a very strange looking distribution that doesn't actually approximate a normal distribution any better. Okay, but this is a transformation that may help value out a little bit on some of these left skewed distributions. And then finally, another common one that I want to mention to you is the arcsine square root transformation. Okay, so quite often you might work with data where your possible values range between 0 and 1. Okay, so you can think about like any number of kinds of data or examples of data where there's no possible value less than 0, no possible value greater than 1, and so you end up with a distribution that looks like this, which is truncated at the ends. Okay, so instead of a set of tails approaching the x-axis asymptotically, you basically have just this big cutoff at the end of the distribution. Okay, what you can do on these ones is take the individual values, take the square root of that value, and then take the arcsine of that value. Okay, I know it's kind of a strange sounding transformation, but what it does is it just sort of evens out or extends the tails of that distribution. Okay, so let me just show you some examples. Okay, so here's a fairly normal distribution. So what do you apply? What kind of transformation to apply? Well, none's necessary here. Okay, but let's look at let's look at log transformations. If you look at this distribution, what you'll notice is it's not bad, but you'll see that it's a little right skewed or positive skewed. If I were to take the individual observations that define this line, okay, you can see this line here. If I take the individual observations that define that line and take the log of those values, I'll get a new distribution that looks like this. Okay, that new distribution better approximates a normal distribution. Okay, so that's improved my assumptions regarding the normality of my distribution. Okay, we can also see the arcsine square root as an example. So here's another example. They don't range in this case between 0 and 1, but you can see again that we have truncated tails. If I take the arcsine square root of these, I get a distribution that still has some degree of truncation here. Okay, it's not perfect, but as you can see, it's a much better distribution than what we had in the previous example, which was this. Okay, so this is our raw data. This is the transform data. The transform data, as you can see, is going to be better suited for parametric tests. Okay, so it's an appropriate transformation to apply here. Okay, so that's and then finally our power transformation. You can see one here that's negative or left skewed. And if I apply a transformation to that data, I get this type of transformation or this type of distribution, and you can see that again, it's not perfect, but it's a much better approximation of a normal distribution. Okay, so that's it for lecture 1, and we're going to be in class doing some activities around these concepts, and we're going to start to learn how to use SAS to determine some of the properties of distributions, including how do we use SAS to calculate means, medians, modes, how do we use SAS to calculate standard deviations, etc. Okay, we'll see you next time. Bye.